Okay, here are the 4 practice problems that we did in class the other day. But before we do, I did want to show you this. I took a screenshot of the reference table, or a portion of the reference table that includes these kinematics equations. So these are all the equations that we've learned and used, and these 3 special ones right here, I would say right in your reference tables. Oh wait, you know what? I'm going to move that over just a little bit. Let's number these equations 1, 2, and 3. So then we can just call them out by number rather than trying to state out the whole equation. We'll use that in this class. That's not, a standard practice. That's just what we're doing in this class. All right, so these are called the kinematic equations. When I am referring to them, these are the 3 that I'm talking equations. Can't see. There we go. The other 2 are just our definitions for velocity and for acceleration up at the top. So we're going to be practicing with these 3. All right, let's take a look at our first question here. A top fuel dragster ran a quarter-mile race in 4.4 seconds with an acceleration of 41.5 meters per second squared. What was his final speed as he crossed the finish line? And what is the length of the race? So 2 things we're going to be solving for. All right, 4.4 seconds. So remember, let's use the LESA method. Let's show all work. So list, equation, substitution, and answer with units. 4.4 seconds. So in my list, I'm going to say t equals 4.4 seconds. We have an acceleration of 41.5. Let me get that right. Meters per second squared. And we are looking for the final speed. That would be VF as he crossed the finish line. Okay, so going back a page here quick. Notice in these 3 kinematic equations, there are 5 variables. There will always be 5 variables whenever we're dealing with kinematics. And so we have final velocity. We have initial. I'm going to write them off to the side. All right, so we'll always have these 5 variables that we're dealing with. Typically a constant acceleration, a time, or a distance or displacement. So those are the 5 variables. And if we look through these equations, equation 1 is missing one of those, right? Equation 1 does not have d for distance in it. It's got the other 4. Equation 2, if you scan through that one, you will see that it has the 4 variables, but it's missing the final velocity. So we won't use that anytime we need a final velocity. And then the third equation, we have VF, VI, A, and D. So there's no time in this equation. All right. So keep that in mind as we go through these questions. All right, so we are looking for the length of the race comes second. So that's sort of the second part. These are, dropped my pencils, my pens. All right, here we go. 2 things we're looking for. We are missing the initial velocity. That would be helpful to know. It's actually, we're not missing it. It just wasn't stated, but this is a drag race. So let's just assume that the initial velocity starts at 0, and then that will make our lives easier. All right, so we have a t, a final velocity, an initial velocity. So let's go, let's use equation 1 for that. So that says final velocity is initial plus a t. All right, and that's sort of just a rearrangement of this equation. If you expand that and rearrange it, it gets you to equation 1. All right, so let's substitute in 0 for the first for VI, and then we have 41.5. Let me get that right. 41.5 and 4.4 seconds. Make sure you're including units as you substitute. Okay, and so what we end up when you punch this in your calculator is you get 182.6, but let's just practice our significant figures. All right, so here has 3 sig figs, and this only has 2, so I should round to 2, which means this would become 183. I can't do sig figs. That would be 180 meters per second. Okay, and now let's answer the second part of finding the distance right here. So let's use equation 2 for that one. Plus 1/2 at squared. The reason I'm using that one rather than equation 3 is because I solved for this, and if I made a mistake, I don't want to accidentally substitute in something that I had done wrong. All right, so this whole first part, well, that's still going to be 0 when I put this in, but I'm going to insert it in for now, just for the first time going through this, so you can kind of see the whole thing. All right, and then the acceleration is 41.5 meters per second squared. And do not forget to square that time. Okay, so this works out to be, I've got something in my way here, but in the calculator, again, it shows up at 401.72, and I can only have two significant digits on that. So I have to call it 400, but to be really precise, I would have to write it as 4.0 times 10 squared because of having two sig figs. So not a big deal. I would probably just write 400 as my answer. Okay, and if you think about it, this is a quarter-mile race. So anyone who does track, you know that a quarter mile is one time around the track, and that is 400 meters. So we know we're okay with that. All right, moving on to the second one. We've got a farmer here. He's clearing land for the runway of his airport. He's building an airport. His plane, he knows, has an acceleration rate that is 3 meters per second squared. All right, so acceleration, A, is 3 meters per second squared. I'm starting to make my list even as I read through the question. The takeoff speed for the plane needs to be at least 65 meters per second. So let's think that through for a second. That is a speed, but which one is it? Is it the final or the initial? Well, he's taking off, so he's probably going to start at 0 as the initial. That means this would be the final velocity of 65. Assuming this minimum rate, what is the minimum allowed length of land he should clear? Okay, so they're asking us to find the distance. All right, and we're gonna actually add in that initial velocity is 0 because we're just assuming he's gonna start at 0 when he drives or when he takes off. All right, so looking through, let's go quick to the, we have A, VF, D, and VI. So go back to the equations quick. And that looks like we're gonna use equation 3 because there's no time anywhere in there. So let me write that. And you must include the equation every time you do one of these questions. You don't want to lose any points for that. All right, so I mentioned early on, let's rearrange this equation for the thing we're solving for. So we are solving for D in this case. So I will subtract the VI over, so it's going to be VF squared minus VI squared. And then I should divide 2A on both sides. I'll divide that over like this, and then that leaves me with the distance. Sometimes it's easier to manipulate the formula first. All right, now I'll substitute. I've got 65 meters per second. That is being squared. And then we're subtracting 0 squared, which is just 0. And we've got 2 and 3 meters per second squared for the acceleration. And that will give us our distance, which when you punch that in your calculator, you end up with 704.1667, like a whole bunch of extras. And we want to round that off. So again, 2 sig fig. No, 1 sig fig right here. So I have to just round that and call it 700. That might be a problem if you're taking off in an airplane. You might want those extra 4 meters. So if I was actually building an airport, I'd probably go maybe 800 meters or heck, just go 1,000. That way it's easier to land as well. All right, moving on. Trying to go quickly here for you. All right, we've got a bullet that's moving at a speed of 300. That's faster than sound, by the way. So this must be some sort of physics-y bullet. We've got a speed, 367 meters per second, when it embeds into a lump of moist clay. So it's coming to a stop. All right, the bullet penetrates for a distance of, that's only 6 centimeters, 6.221 centimeters. Determine the acceleration of the bullet while moving in the clay. All right, here we go. So this speed that it gave us was the initial speed of the bullet, 367 meters per second, and then it's going into the clay and stopping. So that means we have a final velocity of 0, even though it's not stated in the question. We have to make that assumption. All right, and we have a distance of 0.0621 meters. We're looking for the acceleration. All right, I think we're going to end up using the same equation again. I'll write it here. If you can rearrange it in your head, it's not necessarily to show this one step that I just wrote down. You could rearrange it in your head. Like, I'll do this, VI squared, and then I need to divide by 2 and D so that I leave the A over here on itself. All right, so you could just write this down, just like that, and that is 100% acceptable. All right, and I'm going to substitute in. Oh, we have a 0 first. Actually, let's just do this. I'm going to say that whole thing becomes 0. And what I'm left with is minus or negative 367 meters per second. And that is being squared. All right. So the negative is going to hang around. It's not going to get squared away. We'll substitute in our distance. And that will work out to be, oh, that's an A, not a 0. So we're going to end up with negative, a huge number, 1,084,452, and basically non-repeating, non-terminating decimal. All right, it's a huge amount of acceleration. So let's round this to an appropriate number. I have 3 sig figs up here, 3 sig figs there. So it looks like I want it to say 108, but I'm also going to use scientific notation. So I'll put my decimal here. I'm out of space up here, so I'm going to go up to the top. So A equals negative 1.08. And I moved it 6 places, 1, 2, 3, 4, 5, 6 to get there. And meters per second squared. Negative because it's slowing down. 1,000,000 meters per second squared. Wow. All right, and the last one. We have a car traveling at 22.4 meters per second. It skids to a stop in 2.55 seconds. Determine the skidding distance. All right, this is our initial velocity. 22. Something else that's slowing down to a stop. All right, so that means our VF is going to be 0 again. These all seem pretty similar to me. Time of 2.5 seconds. And we're trying to determine the distance. Oh, so right away I see a problem. We need acceleration. I'll go back a couple slides here. And every equation has acceleration in it. So that is not given to us. We have to go find that quick. All right, so from equation 1 or from the definition, we know it's delta V over T. And so I'm going to say acceleration is final minus initial, 0 minus the initial of 22.4 divided by time of 2.55 seconds. And we have an acceleration rate of negative 8.78 when I round for sig figs. It was 8.7843 and change, and I rounded to this. All right, now that I have acceleration, I'm looking for displacement or distance. I think I'm going to go with equation 2 on this one. I'll write it out first, and then I'll substitute everything into the appropriate place. All right, I need a bit of room here. So 22.4 meters per second times the 2.55 seconds. Then we're going to add 1/2 of the acceleration. Keep in mind, this is negative now. So that's going to end up subtracting in the end. And then 2.55 seconds. Don't forget the square. Big deal. All right. Instead of just putting the answer down, I'm going to show you quick what happens here. We've got 57.12 on this half of the equation. Oh, and that's meters because the units cancel. And then we're subtracting away 28.55 and meters on this side of the equation as well. All right, that comes from all of this. So the overall final distance is 28.6 meters. That's how long it takes the car to skid to a stop. Now, as I was getting this ready for recording, I realized there's a shortcut we can do. Instead of doing all this work, I've got a shortcut for you. So let me copy this for a moment here. Copy. And I'm going to go to a new screen here and bring it with me. So paste. All right, there's our data. That's what we were given. There's a real simple shortcut you can use, and it comes from this definition of the average velocity is distance over time. So on the left side, average velocity. If I took my two velocities, in this case, VI, and I added them together and then divided by the number of things I had, in this case, 2 of them, that's going to get me the average velocity. All right, well, this actually works out pretty well because one of those things is 0. So I've got 22.4 plus a 0, divide that by 2. My average velocity is 11.2. So as the car is slowing down, that's the speed it has on average. Well, that just equals the distance divided by the time. So I'm going to multiply my time over, and watch this shortcut. All right, I'm going to multiply the t over. 2.55 seconds. And lo and behold, what do you know? You get the same thing. You get 28.6 or something really close to that when you round. All right, so that was a shortcut, just recognizing that we could do something simple like take the average of those two velocities.